In this video, we're going to have a look at resolving forces and using resultant force equals 0. So it's told you that a particle P of mass 10 kg, so that's very important because what force comes from mass is weight. I'm sure you guys are aware that weight is equal to mg. Now you can find the weight directly, you can do 10 times 9.8, but you can also leave it as 10g. So let's do it like that for this question. It's held in equilibrium, so that's very important itself. So notice how I'm breaking down like each individual part of the question as I'm going, because that helps quite a lot. If it's in equilibrium, that means that there's no motion, so resultant force is 0 horizontally and resultant force is 0 vertically. That's going to allow us to form two different expressions, which I'm sure will be useful later on in the question. It's attached by two light and extensible strings. Light means that there's no friction acting on the strings, and I'm sure you guys already know, but tension acts up the string. We'll call this T and then subscript of A for tension at A, and this T subscript of B for tension at B. It then tells you string B is at an angle of 35 degrees, whereas string A is at an angle of 50 degrees to the horizontal. Then says find the tension in string A. So what I'd recommend you guys do is draw your own sort of particle and label all the horizontal and vertical forces acting on that one particle. So like we mentioned before, the weight which acts vertically downwards would be 10g in this instance. Now this tension at B, it doesn't have a horizontal component yet, but what we can do is form our own right angle triangle. If the hypotenuse of that right angle triangle is the tension at B, then the length that's adjacent to the angle, so the length touching the angle, will always be the force cos of the angle. And that would act to the right, so that this vertical one can act upwards and they can create this arrow direction that it's moving in. So yeah, like I mentioned, this here would act vertically upwards instead of vertically downwards in order for the tension at B to go in that sort of northeast direction that it's going in. Okay, so if the component adjacent to the angle is TB cos 35, the component opposite the angle is the tension or the force sine 25. We can label that on our singular diagram. So we can say that there's a force of the tension of B sine 25 acting vertically upwards. And we can also say that there's a tension of B cos, oh sorry, I just realized I wrote 25 by accident. It should be 35. And then there's tension of B cos 35 acting to the right. Acting to the left would be, well, let's think about this. Similarly to how we split up tension at B into horizontal and vertical components, we can split up the tension of A so that it's tension of A cos 50 degrees. This is cos 50 because it's the sort of component that's adjacent to the angle. So let's write that, tension of A cos 50. And then acting upwards would be the tension of A sine 50. Again, this acts upwards because if it acted downwards, then this tension would be in that direction, if that makes sense. And that would be tension of A sine 50. So let's draw that going upwards as well. So we have tension of A sine 50. Like I previously mentioned, everything is in equilibrium, so the resultant force is 0. Let's start by forming the expression horizontally. If the resultant force horizontally is equal to 0, that means that the force to the left, TA cos 50, would be equal to the force on the right, which is tension at B cos 35. Now, we're at a bit of a dead end because there's two unknowns here, so we can't really go any further with this. Instead, let's focus on forming the other expression, and I'm sure you'll be able to use the two expressions to find whatever you need to find. Since we know vertically the resultant force is also 0, we can say that the sum of the upward forces, so TA sine 50 plus TB sine 35, is all equal to the sum of the downward forces, which in this case would just be 10g. Now that we've got two expressions with tension at A and tension at B unknown, what we can do is make tension of A the subject of one equation and input it into the other expression. So let's do that. We can say that the tension of A is equal to the tension TB cos 35, everything that's on the right hand side already, all divided, cos 35, all divided by cos 50. And then you can input that into the tension of A in this expression here. So let's do that. We'll have, instead of tension at A, we'll have tension of B cos 35 all over cos 50, and then plus tension of B sine 35, just that second term here that I'm bringing across, all equals 10g. Now that we've got an expression with only one unknown, which is tension at B, we can factor out that unknown. So when you do that, you get the tension of B, and then in the big bracket, cos 35 over cos 50. Quite a lot of writing, feel free to skip ahead if you guys would like. Plus what you multiply to tension of B to get to that second term, which is sine 35, is all equal to 10g. In which case tension of B would just be 10g divided by all of this, which I'm not going to write out again, but it's just going to be 63.2 newtons. After you've got the tension at B, although we did part B first, that's completely fine. We can also find the tension at A by just substituting it into any one of these two expressions, or even this one, because this is a rearranged version that also works. Putting the tension of B into this expression, we get that the tension of A would become 80.6 newtons. And that's it. That's everything for this question. As you can see, it's an 8-mark question, quite a lot of working out, but hopefully that makes sense to you guys. Be sure to leave a like if this video did help and subscribe. I'd appreciate it a lot. Thanks for watching and have a nice rest of your day.